All right, so last time we had done section 5.5, which was on inequalities in a single triangle. Like two sides added together are bigger than the third, stuff like that. This is on inequalities in two triangles. So now we don't have just a single triangle. We're comparing two triangles to each other. Okay, I want you to look at these two triangles. Okay, in these triangles, I've marked AB and DE as the same. And I've also marked BC and EF as the same. Okay, so you have two sides that are congruent. But angle B is larger than angle E. Okay? Now, if angle B and E were the same, we could say these triangles are congruent by side, angle, side. But they're not congruent because B is larger than E. So how do you think side AC is going to compare to DF? Look at the size of the angle that's across from AC, and look at the size of the angle that's across from DF. Right? I mean, just take a guess, and then we'll see if we're right or not.
AC is going to be larger than DF.
Yeah. AC is going to be larger than DF. Let's see, is that right there? No. Okay, and this is related to what's called the Hinge Theorem. Okay? What I want you to do is think of AB and BC as two sides of a hinge. Okay? And imagine opening and closing that hinge. Well, since BC and EF match, and AB and DE match, okay, the angle, that's right in the hinge. And the hinge is the same size on both triangles, because the sides are marked as congruent. So imagine taking that hinge and opening it up bigger. Okay? If you open that hinge bigger, you make the angle bigger, and then you make the distance of the third side bigger. Okay? If you make the hinge smaller, then the distance on the third side gets smaller. Okay, it's called the Hinge Theorem. I'm going to give you the page that it's on because it's a lot to write. Okay, everything I just said, that's the Hinge Theorem. It's just hard to describe it briefly in words. Okay, but here's the diagram. Okay, to use the Hinge Theorem, you've got to have two pairs of sides that are congruent, like AB and DE, and BC and DF. And in my picture, since I drew angle B as bigger, think of that hinge as being open more. That third side is going to be longer. Okay? That's the Hinge Theorem. Okay, so let me give you the page that's on. Okay, so Hinge Theorem is on page 303. Bless you. And again, it is a lot to write down, so you might just want to, if you write it down, you might just want to write it the original way, and then right below it, the converse is also true. I have the converse all written out, but that's just as much to write. Okay, so the Hinge Theorem says, if two sides of one triangle are congruent to two sides of another triangle, okay, that's the first part. Two sides of one triangle are congruent to two sides of another. And the included angle, that means the angle that's right in the hinge, the angle that's between, or the angle that's formed by the two sides that are congruent. Okay? And the included angle of the first triangle is larger than the included angle of the second. Okay, what that means is that third side is going to be larger. Okay, let me go back. All right. So, and we said, and the included angle of the first triangle is larger than the included angle of the second. That means the hinge is open more in the first triangle than it is in the second. Then that means the third side in the first triangle, the one where the hinge is open more, is going to be longer than the third side in the second triangle. Because in the second triangle, think of the hinge as being closed a little more. So that distance is going to be a little shorter. Okay? So again, if two sides in one triangle are congruent to two sides of another, and the included angle in the first triangle is bigger than the included angle in the second, then the third side of the first triangle is bigger than the third side of the second. Okay? That's the Hinge theorem. Okay? It's a lot to kind of explain, but the basic idea is think of that hinge. Okay, and below that, just write down that the converse is also true. Okay, the converse would be if you took the if and the then and you switched them. Okay, but it's going to be a lot to rewrite all that. Okay, so let me show you what, does everybody have down what the Hinge theorem is? Okay, let me show you the converse, just so we can see it. So it still starts out with if two sides of one triangle are congruent to two sides of another, but this is where it switches. Instead of starting to talk about the angles and then talking about the sides, it starts off by talking about the sides first and then the angles. So the idea here is if you've got, let me put it up, but again, just write down the converse is also true. So the converse says you've got two congruent sides in a triangle, okay, and the third side is bigger in one triangle than it is the other, then that angle across from it is going to be bigger in that triangle than it is in the other. Okay. So if that hinge is open more, the side is longer, that means the angle is bigger. If that side is shorter, then the angle becomes smaller. Okay. So the converse of the Hinge theorem is also true. Everybody has down just this part right here at least. That's all you really need. All right. Let's look at an example. Okay, first thing you want to do when you look at it is decide, okay, does the Hinge theorem even apply here? And it does. How do I know? I've got two pairs of congruent sides. DE and AB match, EF and BC match. Okay, so we can use the Hinge theorem. Okay, let's say I didn't even give you choices. What do you know about DF compared to AC? Well, you actually know the length of AC. So you could guarantee me something about DF based on the Hinge theorem. Yep?
DF is going to be larger than 12.
It's got to be bigger than 12. Okay? This hinge in the first triangle is open more than the second. So if it's open more than this one, it's open more than 12. It's got to be more than 12. So what's the only number there that would be even a possibility for an answer? 23. How could it be equal to 12? What would angle E have to be to make DF exactly 12? We could answer that. I don't know if 23 is exactly right here, but yep.
The angle would have to be 36.
Right. If angle E was 36, then these triangles would be congruent by side angle side. Then DF and AC would be the same. Okay? But in this case, we're using the Hinge theorem. Any question on how we got 23? Just think of that hinge at E. It's open more than the hinge at B. So it's got to be bigger. DF's got to be bigger than 12. Okay, this is the same thing, except this time I wrote it out in words and I didn't give you the diagram. What do you think is easier to visualize? The diagram or what I've written in words?
Diagram.
Yeah, the diagram. Okay, so what I would do right away is try to draw your triangle. Let's call that RST. And let's call this one XYZ. They're telling me RT and XZ are congruent. And they all, let's do it in, Okay, so RT and XZ are the same. ST and YZ. Okay, right away I know the Hinge theorem applies. Okay. And now they're telling me that RS is 3.7 and XY is 4.5. Okay, what else do they tell me? Angle Z, 75. What do you know about angle T?
It's going to be smaller than angle Z.
It's got to be smaller, right? Look at the hinge. RS is shorter. The hinge is open less at T than it is at Z. Okay? 3.7 versus 4.5. So T's got to be smaller than 75. So the only choice there that makes sense? 60. Okay? So you couldn't figure it out. Like if I just gave you that and I didn't give you any choices and I said how big is angle T? No, you can't. The Hinge theorem can't figure that out. But in a multiple choice question, it can be used to eliminate possibilities like we just did. Okay, any question on that one? Everyone get that concept of the Hinge theorem? Basic idea? Okay, so this one is a fill in the blank, either a less than, a greater than, or equal to. Okay, first of all, does the Hinge theorem apply here? And if it does, tell me, how do you know that? Oh, Dakota? No? Okay, why not? What do you have to have for the Hinge theorem? Either the converse or the regular one. How does it start out? If no, not angles. Anyone help? How does the Hinge theorem start out? Anyone help him out? If well, how about Alyssa?
Two sides.
If two sides of
One are congruent to two sides of another.
yes, if two sides in one triangle are congruent to two sides of another. Do we have that here, Dakota? What do you think?
Yes.
Do we have two sides in one triangle marked congruent to two sides in another? Yeah, we get tick marks, right? We have a single tick mark on each side. That's one pair. On the hypotenuse, we have two tick marks on each. So we have two pairs of sides that are congruent matching up. So yes, the Hinge theorem does apply. So how would angle 1 and 2 compare here? It would be less than, greater than, or equal. What do you think?
Equal.
Yeah, it would be equal. How come? Because what?
They're congruent.
Okay, well, we have two pairs of sides, but we don't. Anyone else tell me, how do you know angle 1 and 2 are congruent? This is actually something we did earlier on. Yeah?
The angle where the hinges are both 90.
Okay. So the angle where, well, the hinge is actually at the number. The hinge is, so yeah, if you knew that, that'd be a little different. But the hinge in this case is the number, not the 90. So it's a little different, but we can still figure out they're equal.
So then use the hypotenuse like there.
Perfect. It's the HL theorem. Good job. The hypotenuse leg theorem says if you've got a hypotenuse and a leg in one triangle, congruent to a hypotenuse and a leg in another right triangle, then the triangles are congruent, which means everything matches. All the sides, all the angles. Very good.
One time I just think that congruent mark is a poorly written.
Well, they'll make it clear on the test for you. So very good, hypotenuse leg theorem. Okay, how about this time? Same directions, less than, greater than, or equal to.
It's equal.
Yeah.
Whatever side that is equal, it's equal to itself as a reflection property.
Right. I don't know if I drew these as separate, but no. If you looked at it, it's two separate triangles. That side matches that. That side matches that. So your hinge is right where the numbered angles are. So now compare the third sides. They're equal. Well, if the third sides are equal, then the angles are equal. Okay? You could also say these triangles are congruent by side, side, side. Two triangles that are congruent, everything's equal. Yeah.
Like I said, you could say it because of CPTC.
Yeah, exactly. When you have congruent triangles, corresponding parts are congruent as well. Yep. Okay, so you didn't even really need to use the Hinge theorem here, but you could have. Okay, you could have. Okay, and let's do one more in this section, and then we'll move on. Okay, so I want to use an inequality to describe the restriction on the value of x. Okay, do we have a Hinge theorem problem here? Do we have, look for one side in a triangle that matches another, and then you've got to find another pair. So you have to have two pairs of congruent sides. Do you have that here?
Yes.
Yeah. You've got this side matching itself, okay? And then you've got 8 and 8. So you could say this side matches that side. So the hinge is right at the number. Okay? Just that side with the double tick mark is used, it's used in each triangle. So what do you know about x? The size of x. It has to be, look at the angle across from x. Look at the angle across from 9. So you know how x is going to compare to 9 by looking at that angle. Katrina? Yeah. 60 is smaller than 70. Okay? So we know that 9 is going to be smaller than x. Or you could say it the way Katrina said, if 9 is smaller than x, that means x is bigger than 9. Okay? What is x? We don't know. The Hinge theorem doesn't actually help us find that. It just tells us it's bigger than 9. Okay? Okay, any questions on that? If we knew a little bit of trig, we could probably find x.
X is 10, isn't it?
Is x 10?
Wouldn't it be 10? Because if two sides are equal, right, and then it goes up about 10 degrees, you go up 1.
Well, it's a good guess. You might think if it goes up 10 degrees, the side might go up, but we don't know exactly how much the side goes up for 10 degrees. Yeah. But we might be able to use some trig and find that, but that's not something we'll be studying this class. Okay. Any other questions on that? Okay, so that's the Hinge theorem. All right, so everything we've studied in chapters 4 and 5, that all had to do with triangles. Okay, three-sided figure. So now we're going to start to look at polygons. Okay, a lot of times we can take a shape that's a polygon and break it down into triangles and use facts we already know. But we're going to start talking about shapes with more than 3 sides. Okay, in your book, this is, let's see, page 3, it's around 320. Yeah, 320, 322. They give the definition of a polygon. Okay, first of all, anybody know what that prefix means, poly? Yeah. Well, a polygon is going to have something to do with a shape being closed. But just the word poly in and of itself might have heard the word polyphonic. It means something. It's a cell phone term. Yeah. Yeah, more than one, many. Okay, so if you have like a older cell phone, they could only do so many ringtones. They called it like a polyphonic ringtone, meaning it could do many tones rather than just a normal ringing sound like you hear. All right, what else? So there's all kinds of words that have the prefix poly. When we get to studying 3D shapes, we'll talk about polyhedrons. Polyhedrons are very similar to polygons, except they're 3D instead of 2D. Okay, so the idea of a polygon is it has to be formed by 3 or more segments. Notice here, it's segment. Segment is a straight. It can't be curved. Segments, those are arcs. Okay, if something's curved, it's an arc, not a segment. So it has to be formed by 3 or more segments. Those are called the sides. And no 2 sides with a common endpoint are collinear. Okay, so that part's a little weird. No 2 endpoints, or no 2 sides with common endpoints are collinear. Okay. Yeah, what that would mean is, let's say you had 3 segments. You could do something like this. There's 3 or more segments. Those are sides. But that's not a polygon. Okay? Because now you've got a segment that has common endpoints, and they're collinear. Okay, that's not a polygon. That's actually a segment, right? 3 segments. Yep. And each side has to intersect exactly 2 other sides. So I could draw something that fits definition, the first part of the definition, but not the second. Okay, watch this. Okay, according to definition 1, I've got 3 segments. Do I have any sides that are collinear here? Nope. But now this is where the second part comes in. It says each side has to intersect exactly 2 other sides. Well, that shape doesn't do that. Okay, first of all, in the middle here, we've got 3 all intersecting, not 2. Okay? And then up at the top here, we don't have any intersecting that point. Okay, so each side, basically for each of one of these dots, it has to have 2 segments going into it. This one only has 1, this one has 3. That doesn't work. Okay, so think of a square. Okay, that fits the definition. You got 4 segments, no 2 sides with common endpoints are collinear, and for each vertex, which is what these are called, there's 2 sides going into it. Okay? So that's the definition of a polygon. Any question on that? Okay, something like, let's see, this would not be a polygon. How come? What part of the definition does that one fail? Yeah.
It's not closed.
So which part, is that part 1 or part 2?
Part 1. Part 2. Part 2.
It's part 2. Each side has to intersect exactly 2 other sides. Well, those 2 vertices don't. Okay. If you drew in a third one, now you're good. Get 2 segments coming out of every vertex. Okay, I've already been using this word, but each endpoint of a side, that's called a vertex. And the plural, that's your vertices. And you can name a polygon by listing its vertices consecutively. We've already done this with triangles. Triangle ABC. The only thing is, in a triangle, there's no way to name the vertices non-consecutively. That's impossible.
are next to each other.
They're all next to each other, right? You can take A, B, and C and name them in any order you want. And it's always going to go around in a clockwise or counterclockwise direction. BCA, ABC, CAB, doesn't matter. But once you start to add in more sides, then you got to be careful how you name it. Okay, you want to name it consecutively. You can go clockwise or counterclockwise, doesn't matter. Okay, so this would be called polygon ABCDE, or you could call it polygon CDEAB. Doesn't matter. Pick a vertex and name every other one going around, clockwise or counterclockwise. Okay, we could actually be a little more specific. Does anybody know what kind of polygon ABCDE is? It's a pentagon, right? So we're gonna go over those prefixes in a couple minutes. Okay. Everyone understand the idea of how you name a polygon? All right. So what I'm going to do is I'm going to give you some shapes, and I want you to just tell me whether or not you think they're polygons. Okay.
Oh, it's a Star Trek.
The Star Trek symbol. There you go in the upper left. Yeah. Is that a polygon?
Yes.
Sure. It meets. There's a curve like that.
Yeah, just like,
Each one of the
talking about the Star Trek.
this symbol. Yeah. Each side. I mean, pretend like they're all straight.
okay.
We didn't say that a shape can't kind of cave back in on itself. That's okay. That's still considered a polygon. It's a different kind of polygon, but it's a little different. So this is a polygon. Okay. How about the next one? The one on the right. Is that a polygon? Yep. That's fine. Okay, it meets all the criteria for those definitions. Okay. How about the one in the lower left? Is that a polygon?
No.
Well, let's look. If you mark all the vertices,
Oh, okay.
does each vertex have two segments going into it?
Yeah.
Yep. Are there any curved segments here? No, nothing's curved. And is there at least 3 segments in that picture? Yep. In fact, that's another pentagon. How about the last one? No. Yeah, what's wrong with this one? Yeah, it's curved. Okay. The definition said segment, not arcs. Okay, it's got to have segments. Okay, so that last one is no.
I wonder.
Oh, actually, 2 more. How about this one? No.
All the pigs again?
What's wrong with that one? Yeah, it's not closed. And another way to say that is definition, the second part. Each vertex doesn't have 2 segments going from it. Okay, the one in lower right does, lower left does, but the other ones only have 1. Okay, how about this hourglass kind of shape? Is that a polygon? Let's mark my vertices.
No.
No, that's not a polygon because it's all segments. There's more than 3, but each vertex doesn't have 2 coming from it. This one does, that one does. Yeah, the one in the middle has 4. Okay, that can happen if things cross. Okay, so in general, if segments cross each other, that will mess up the definition of a polygon. No. Okay, any questions on that? So there's some examples of shapes that are and are not polygons. Okay, so when we name a polygon, generally we name it by the number of sides it has. Okay, let's start with 3. If a polygon has 3 sides, what name do we give it? Triangle. Or, what's another name? Because a lot of the shapes we use end in gon. Pentagon, octagon, hexagon, things like that. There is a name that ends in gon for a three-sided. We don't use it as much. We use a triangle. A trigon, yeah. Okay, triangle or
Gosh, I was just
trigon.
guessing now. I have no
told you.
Yeah, we generally use the word triangle though. How about four sides? There's two names for shapes that ends in four sides. There's the one most people use, and then there is one ending in gon, but that one's a little harder to guess. Well, square is a specific type of four-sided shape. Yeah. Anybody know what a four-sided shape is? What it's called? Yeah. Okay, quadrilateral. That's one name. That's the most common name.
Quadrilateral.
How about, yeah, it's a little different. Anybody know there's another prefix that has to do with four besides quad? Quadrilateral, that's that one. Anybody know another prefix? It has to do with a game. Anybody know what?
Tetris?
Tetris, yeah, tetra. Okay, tetra.
Sorry.
What's that? How's that?
Tetragon.
What's the
Okay.
Tetris song go?
So if you've ever noticed when you play that game, all the shapes, they have four blocks. They're arranged, different ways.
No. It's called a tetra.
What's that?
No,
Yeah, they all have four.
some of them have three.
No, they all have.
I think there's one that looks like this or something, or
No, you
I don't know how it looks.
Which one has
Three?
The L has three?
No, there's one that's like
One, two, three.
Doesn't the L look like that? Doesn't it have four?
Yeah.
Yeah, I think they all have four. Yeah. So tetra is another prefix that means four. So tetragon. For the rest of the shapes, we pretty much just have one name. We already said it for a five-sided shape. Yeah. Pentagon.
Oh, and I was going to say,
Yeah.
those little tetra shapes are called tetragonals.
Is that what they're called? The different shapes? Yeah, tetra means four, and then four of those little shape things, blocks. How about six? Anybody know six? Yeah. It's a hexagon. Okay, how about seven? Okay, so there's two prefixes that mean seven. When we're counting, the prefixes we generally use, like you start out with million, billion, and then trillion, tri, there's your tri. And then four is quadrillion. For five, though, when we're counting, we use a different prefix. It's called quintillion. For six, when we get to six, that's sextillion. So there's different prefixes when you're counting and then when you're naming the shape. And that happens with seven. There's hept and sept. Okay? So when we're counting the number of sides and naming the shape, we call it a heptagon. But if you were counting, you would say septillion. So that's where it gets kind of confusing. Why they have different prefixes, I don't know. But for 8, there is just one prefix for 8. Whether you're counting or you're naming a shape, oct. So if you were counting, you'd say like octillion or octagon for the shape. So 8's an easy one. 9, yep, prefix non. Okay, so if you were counting with numbers, you'd say like nonillion. With a shape, it's nonagon.
What is non-alien?
Non, that's the prefix meaning 9.
Doesn't that mean X?
What is
If it's not a shape, it's an X shape.
How about 10?
Like what in the universe is even that big?
Oh, why would you would count numbers? Well, if you were,
That's that big?
we use scientific notation. We don't really name numbers using these prefixes a lot.
Yeah.
We'd say like something like if you're talking about the number of molecules or atoms in them. I know there's, what's this number? Avogadro's number? 6.02 times 10 to the 23rd? In chemistry, it's from chemistry. So that's a number that has over 20-something digits, but you just write it in scientific notation. We don't use these prefixes. How about 10? What's the prefix for 10? Yeah, dec. So if you were counting, it'd be decillion, D-E-C.
Decade.
Or decade, dec. Or decagon. Good. know what an 11-sided shape would be called. I know if you're counting, you call it undecillion. And then duodecillion, tridecillion, quaddecillion. So there's a pattern to it. But when we get into 12, that's dodecagon. 12-sided shape is a dodecagon. And then beyond that, if we have a 15-sided or 16-sided shape, you could just say 15 gone, 16 gone. You just say it like that.
72 gone.
N gone, yeah. Yeah. Although there probably is a name for that, but we don't use it. 72-sided shape.
Probably endless. There's probably just certain prefixes are combined.
Yeah, you just keep combining the prefixes, and it is endless.
And
Yeah. All right, so the last thing I want to look at is, it has to do with that shape we looked at right here. Okay, we had a shape that kind of caved back in on itself. Okay? And that gets into what's called a concave or a convex shape. So a polygon is convex. Okay, a polygon is convex if you could put a dot on the perimeter anywhere you want, 2 dots, and then you connect that line segment. If you connect it and it's completely inside the shape all the time, then that's called convex. Okay? Both of these shapes are convex. No matter where I put a dot, I can put dots anywhere I want. If I connect the 2 dots, the segment that connects them is always going to be completely inside the shape. Right? Put one here and here. There's no way for me to ever draw a segment that would go outside the shape. Okay? That's convex. Okay? If a polygon isn't convex, then it's concave. Okay? Concave, think of the cave part. It kind of caves in on itself. So it's possible that I could draw a segment that's contained inside, but it's also possible for me to draw a segment that goes outside. And if I put a dot here and here, or if I did one here and there. If I connect that segment, part of the segment goes outside the shape. Okay, if that happens, that's called concave. And the simple way to think of it, one side kind of caves in.
think of it like a soap. You know when you push on it?
Yeah? So concave and convex, those are terms that you're either one or the other. You can't be both. If you're concave, you're not convex. It's one. It's like a true false. It's either one or the other. Yeah.
Well, do they have canned water anywhere?
I don't know.
Yes.
Overseas?
Yes, they
Maybe.
do.
Overseas?
Okay, but anybody have any questions on concave or convex? What those polygons are? So now when you describe a polygon, you could be a little bit more specific. You could say something is a pentagon, or you could say it's a convex pentagon, right? Or it's a concave pentagon. Okay? So convex and concave can apply to any of the shapes we just talked about. Concave quadrilateral, convex quadrilateral. In fact, this is a concave quadrilateral. It's 4 sides. Okay? How about this shape on the right? It's a concave what? Concave hexagon. Yeah, 6 sides. That's a convex quadrilateral, and then a convex quadrilateral. Okay, so let's try the same thing here. I want to know the type of polygon, and then I want to know if it's concave or convex. Okay. I like to start out with that. Okay, one on the left. Concave or convex? Yep, concave. Think if you drew in a segment like that. Part of it goes outside the shape. It's concave. Okay, concave what? Yeah, that's an octagon. Has 8 sides. 1, 2, 3, 4, 5, 6, 7, 8. So remember your prefix is oct for 8. How about the shape on the right? Brian, concave or convex?
Convex.
Yep, that's convex. It's convex, and what kind of shape is it based on how many sides it has? Yep,
Heptagon.
pentagon, good. Convex pentagon. Okay, so be careful with the prefix for 5. It's a little different when you're counting than when you're naming a shape. All right, so the first part of the homework, that's on the Hinge Theorem. And the second part is on naming shapes. It's pretty quick. So page 305, 7 to 13 all, 15, 19, 32, 35, and 38.
I'll just get my robot.
And on page 325, it's 12 to 22 all. Okay, for the MCAS, let's take a look. Okay, there's 11 multiple choice this week instead of 12. So let's just we'll do 1 through 4. On the multiple choice.